our last electronic systems element that we're going to look at are op-amps. So op-amps have a lot of different things you can do with them. You can do mathematical operations like addition and subtraction. You can amplify signals, which I suppose you could think of as multiplication. You can integrate signals, and I mean literal integration like in calculus or differentiation. And you can do filtering, where we take a portion of frequency range and we remove it from the signal. So we can do all sorts of wonderful things with op-amps. Mostly they work like this. We've got the inverting and the non-inverting terminals, the minus and the plus there. We've got two power supply terminals, V plus and V minus, because we've got to provide an external supply. This thing is an active element. And we've got an output. And so you've got your standard 8-pin PDIP output like that. You've seen this one in lab. So what happens is if E plus, the non-inverting input, is greater than the inverting input, then the output goes positive. If the inverting input is greater than the non-inverting input, then the output goes negative. And these go linearly with some gain G sub O times the difference. So an op-amp amplifies the voltage difference between the terminals. How does it look? It looks a bit like this blue line. If we take the voltage difference, then when the voltage difference is positive, it's going to follow that slope, GO, all the way up to some upper limit, and that upper limit is going to be based on how much supply voltage you give it on the V+. So when it reaches that limit, it can't really go any higher because that's as much energy as you've put in, so it saturates. So this is why we always have to worry about, did we set our voltage limits on the V plus and the V minus high enough? Well, not too high because we don't want to damage our op-amp, but high enough that our signal is not going to be clipped or saturated here. So we need to make sure we're operating kind of in that linear range. What happens internally? Well, we kind of model it like this. We say that there's a resistor between E minus and E plus, and that resistor is infinitely big. It's not really infinitely big, but it's somewhere in the order of mega ohm. And there's going to be a current supply in there that's going to control the output voltage through the output resistor to match what it should be magically when we go through our golden rules. What's it actually inside there? Well, it's really complicated. But this is a 741. You can see that it's got transistors, it's got resistors, it's got capacitors. It's got a lot of fun stuff in there, but the sections that are going to be in there in blue are an input differential amplifier, which, flip back here, is kind of that resistor, and an output amplifier, which is kind of that supply plus a resistor. So those are the big sections. When we talk about an op-amp, we make some big assumptions typically. We'll talk about the open loop gain, the GO, being infinite. That's not true, but it's typically 10 to the 4th to 10 to the 6th, which is a lot of gain. That's a really big gain. We also talk about the input impedance, that resistor between the two inputs, being infinitely high. Well, it's not really, but it's typically on the order of 300 kiloohms to 1,000 gigohms, which is really big. We talk about the output impedance, that resistor between the current source and the output, as being really low, close to 0. And it's typically between 10 ohms and 5K, which is 5K is awfully high. I'd say usually 10 to 200, which is pretty low. And we'll also talk about the bandwidth being infinite, which it's not, but close enough, and the offset being 0, which don't worry about that in this class. The big catch is that we don't use them in open loop mode. We always have feedback on them. So we'll always have something like this, where one of the terminals is connected through a resistor or a wire to the output. That's our feedback. So in this case, we put in a V in to our plus, and we have our negative connected around to the output. And so if you apply the golden rules, then you'll see that V plus and V minus should be the same, which is V in, and V out is directly connected to V minus, so V in must be V out. This is what we call a follower circuit. All it does is it takes advantage of the infinite input impedance at V plus and the 0 output impedance at V out. And so it allows us to separate two systems through the high input and the low output impedances. And so there's no loading on the system, which we'll talk about that. So our golden rules are this. The first golden rule is that the inputs draw no current, and the inputs are V plus and V minus, the non-inverting and the inverting inputs. We said that no current goes into those terminals. They are infinitely high resistance impedance. No current goes in. The second golden rule is that the inverting and non-inverting inputs are at the same voltage. They've got exactly the same voltage, and that'll help us in our calculations. And so the output, because we're in a feedback mode, is going to do whatever it takes to maintain that voltage difference being zero. It's going to always drive it back to zero. So that current source that we talked about being in the output, that's going to go up or down as necessary so that the current keeps the voltage at V plus and V minus the same. This is only true if you've got negative feedback and if you've got everything within spec, but we're typically going to do that. So let's look at an example. We've got an inverting amplifier, so we've got a resistance at the input there, Ri, we've got a resistance at feedback, Rf, and we know that our golden rules are V minus equals V plus. That shouldn't be equal 0, that's a typo. Well, it is equal 0 because, sorry. This portion is the golden rule. It's equal 0 because it's tied into ground. I just put that a little too early. We do know that the current into each of those is equal to 0, and that is the golden rule. So what we can do is we can apply Kirchhoff, and we can say the input current into this node right here is going to be equal to the feedback current plus the current going into the inverting input of the op-amp, which we know, again, that term is 0. And so if we then apply Ohm's law on each of the resistors, Ri and Rf, and we know that we're going to deal with a complex version, which is Z for impedance, then we know that going across Ri is going to be Vn minus V minus over Zi, and going in the feedback, we'll say it's V minus minus V out over Zf. Well, we know that the Z's are actually R's in this case because there are no capacitors or inductors. So V out over Vn must be negative Rf over Ri, which is our inverting amplifier. We could also write it as V out is negative Rf over Ri times Vn. So it amplifies with a gain of Rf over Ri, and it inverts in that it's negative. We can do the same thing with a non-inverting amplifier, and this is where my typo is definitely wrong. Oops. So V minus is equal to V plus. I plus equals I minus equals 0. And so I can work through this, and I'll say that Vn is going to be Ri over Ri plus Rf times V out. So V out is Ri plus Rf over Ri times Vn. And that is, put a different way, 1 plus Rf over Ri times Vn. And that is the output for my non-inverting amplifier. If you don't see it, go back and apply Kirchhoff's law. Let's see. You can apply Kirchhoff's law here, and you should be able to, and Ohm's law, and you should be able to see this pretty quickly. We can do this for a low-pass filter or a high-pass filter as well. The difference between the filters and the amplifiers we just looked at is we're going to include a capacitor. So if we put a capacitor in parallel with our feedback resistor, and we did this in class, then we can talk about the complex impedance, ZF, as being the parallel connection of RF and CF. So if we do that in parallel, think back to your circuits and electronics class, it's going to be the reciprocal of the sum of the reciprocals of the impedances of each element. So 1 over quantity, 1 over RF, plus the reciprocal of the impedance of the capacitor, which is in this case CF j omega. So altogether, the complex feedback impedance is RF over 1 plus RF CF j omega. So, just like before, we can find the output over the input, which is negative RF over Ri times 1 over RF CF j omega plus 1, which, you'll notice, is frequency dependent. And since you've learned about frequency response, you can work out the frequency response of this filter. But think about this portion as being K. think about this portion as being tau, and this is just a k over tau j omega plus 1. This is just a first order RC filter. We can do the same thing with a high-pass filter. We'll put the C in series on the input term. Then we'll talk about the input impedance being, in this case they're in series, so we're just going to add them up. Ri plus, and the impedance of the capacitor is 1 over Ci j omega. So the total impedance will be Ri Ci j omega plus 1 over Ci j omega. And just like before, output over input is going to be negative Rf over Ri, Ri Ci j omega over Ri Ci j omega plus 1. So this one's a little different. This is going to be a K times, in this case, tau j omega over tau j omega plus 1. So this one is a first order system plus a differentiator. It's a little different. You can still work out the frequency response in this. So that's how we deal with op-amps. Op-amps are going to be great for changing the gains on signals. They're going to be great for filtering signals. They're going to be great for adding signals. They're going to be great for separating signals out by acting as a follower. Op-amps are great for signal conditioning. So we've talked about diodes, we've talked about transistors, and we've talked about op-amps. We should be all set to talk about analog to digital conversion, digital to analog conversion, and sensors and actuators.